We're on part 2 of how we know God is real. We're on part 2. And we're based in the book of Romans, chapter 1, verse 20. We read this last week. For since the creation of the world, God's invisible attributes, his eternal power, and his divine nature have been clearly seen, being understood through what has been made. So they're without excuse. People should know that God exists. Even if they didn't have the Bible, the benefit of that. They can see nature, they can see themselves, and you can tell someone must have made this. So we want to get back into this again. This is the argument from design. We talked last week about the same argument, namely that if there's a presence of design, then by definition there must be a designer. That's what design means. And secondly, that our world manifests the presence of design. Well, here's this. So the first premise is not really objectionable to people, but this one here, okay, how would we know that it's design? Maybe it's just apparent design, but not really. Some things can come out in nature looking as though they were designed, but they're really not. And so we have to be very careful that we're really seeing authentic, true design, and that's what we want to look at tonight. Again, last week we looked at the origin of the universe and the fine-tuning of the universe, and the argument was that, this is not a coincidence. This is not something that just happened. That it's way easier to believe in a creator than it is to believe in trillions of invisible universes, which really don't even answer the problem even then. And so, I stand by that. But tonight we're going to shift and look at something different, the natural origin of life. Plausible, believable, that life could have originated naturally, not supernaturally, but just by the forces of nature and random collisions of compounds and molecules. Energy, physics. Plausible, believable, or implausible, not believable. I'm going to argue to you that it's implausible. And here's why. Let's listen to John Lennox, professor at Cambridge, British scholar. Even the tiniest bacterial cells weighing less than a trillionth of a gram is a veritable micro-miniaturized factory containing thousands of exquisitely designed pieces of intricate molecular machinery made up altogether of 100,000 million atoms, far more complicated than any machine built by man and absolutely without parallel in the non-living world. There's just nothing else like it. He says it's hard for us to get any kind of picture of this seething, dizzying, complex activity that occurs inside of a living cell, which contains within its lipid membrane maybe 100 million protein molecules of 20,000 different types, and yet the whole cell is so tiny, a couple of hundred could be placed on the dot of this letter I, which in the original book was quite a bit smaller than that dot there. Cells are astonishingly complex. And a lot of people are not fully aware of just how far out the operations, the organelles of the cell are. Of course, natural origin of life theorists would argue that this is a modern, complex cell. The first cells would have been much simpler than this. And maybe a tenth of that. But it can't be too simple because they have to be able to do what living organisms do. First of all, they have to be able to self-propagate. If they're not multiplying, then how can the process of evolution ever take place? It would just sit as a dormant entity and has to reach the point where there's replication. And that is a mouthful there. Everything we know about self-replicating life is astonishingly complex, as we shall see. It also has to be able to feed, to take in nutrients, and it has to be able to metabolize those nutrients into energy that drives the activities within the cell. It has to be able to fabricate proteins and other compounds with those nutrients. That's really saying a mouthful. We're going to look at what does it take to fabricate proteins. They don't just happen. They have to be fabricated in an elaborate system, a machine. All of this requires information. at an astonishing level. Information, yeah. Let's look at this as a pile of cut granite blocks, okay, big old pile. And so we've assembled these granite blocks. Beneath them, we're going to insert sizable charge of explosives. When we detonate the explosives, the rocks are thrust upward into the air, and when they fall back down, they're going to fall into a shape roughly like this. Don't think so, huh? Why are we intuitively certain that that's not going to happen? It's because the Taj Mahal is designed, okay? And design includes information. These stones have a specific relationship to each other that's quite detailed. If we did, but then we could say, okay, yeah, but we're not just going to do it once. We're going to do it like 10 billion times. And then one of those will come out like this. Again, nope. Not going to happen. If we blew up that pile, we would get something like this. A random blast pattern. And, you know, if we did it a billion times, it would slightly change some of the details, but really look pretty much like that every single time. That's what randomness looks like. And the Taj Mahal is what design looks like. Terrific, and scientists speak of this in terms of information, meaning, for instance, if you laid out a blueprint for the Taj Mahal, it would detail where every piece of it is supposed to be, and then builders would have to follow that blueprint to assemble a building like this. We're going to be looking at designs that dwarf this, that are many millions of times more complex than that building, and even many millions of times less likely that they would ever come about any way other than special creation. Even the simplest life. Scientists have spent a lot of time trying to find and also to imagine how simple a cell could possibly be and still be alive. It ain't that simple. You're still into several millions of atoms in the simplest imaginable cell. The information is still necessary, and that, see, the thing is, information is non-material. It's not something that can be affected by natural forces. It's the product of thought. It's the product of planning. When we're using information here in a specific way, it has to be functional information that relates to the task at hand. Of course, in information theory, you can take a pile of gravel, and it's extremely information rich. If you try to describe that pile mathematically, it's extremely difficult and complex. But it has no function, and that's not the kind of information we're talking about. We're talking about information that actually accomplishes a specific task, the construction of a living cell. And that is a whole different game. Biologically significant polymers neither exist nor replicate themselves apart from specific information. They're not lying around these large, elaborate molecules that make up life. Okay, we're probably all familiar with DNA. Here's a little 2-minute reminder on the DNA transcription. Watch the first molecules in this clip.
What you are about to see is DNA's most extraordinary secret. How a simple code is turned into flesh and blood. It begins with a bundle of factors assembling at the start of a gene.
Those are called enzymes.
A gene is simply a length of DNA instructions stretching away to the left. The assembled factors trigger the first phase of the process, reading off the information that will be needed to make the protein. Everything is ready to roll. 3, 2, 1, go. The blue molecule racing along the DNA is reading the gene. It's unzipping the double helix and copying one of the two strands. The yellow chain snaking out of the top is a copy of the genetic message, and it's made of a close chemical cousin of DNA, called RNA. You are watching this process called transcription in real time.
Real time.
It's happening right now in almost every cell in your body.
That's really fast. Whoa. And then that RNA sails off. The next thing you know, it has to be translated into the protein that it's coded for. And so we have the next process.
When the RNA copy is complete, it snakes out into the outer part of the cell. Then, in a dazzling display of choreography, all the components of a molecular machine lock together around the RNA to form a miniature factory called a ribosome. It translates the genetic information in the RNA into a string of amino acids that will become a protein. Special transfer molecules, the green triangles, bring each amino acid to the ribosome. The amino acids are the small red tips attached to the transfer molecules. There are different transfer molecules for each of the 20 amino acids. Each transfer molecule carries a 3-letter code that is matched with the RNA in the machine. Now we come to the heart of the process. Inside the ribosome, the RNA is pulled through like a tape. The code for each amino acid is read off, 3 letters at a time, and matched to 3 corresponding letters on the transfer molecules.
Codons.
When the right transfer molecule plugs in, the amino acid it carries is added to the growing protein chain. Again, you are watching this in real time.
Yeah.
And after a few seconds, the assembled protein starts to emerge from the ribosome. Ribosomes can make any kind of protein. It just depends what genetic message you feed in on the RNA. In this case, the end product is hemoglobin. The cells in our bone marrow churn out 100 trillion molecules of it per second. And as a result, our muscles, brain, and all the vital organs in our body receive the oxygen they need.
Oh my God, did she say 100 trillion of those per second in each person's body? Man, that's amazing. And so, okay, is all that really necessary? Here's what we know. All life that we see works that way. This genetic code, in fact, is the same all over the world, all different species. It's really no different. And we never see examples of these. You know, hemoglobin is a pretty elaborate polymer that's got a lot of atoms in it, arranged a very specific way. The arrangement is crucial to the functioning of the protein. And so it's not just going to happen. You can't shake up a bottle of the amino acids and have something like that pop out, any more than you could have the Taj Mahal come out of that blast. Let's zero in a little bit closer to that first part where those enzymes locked around the DNA chain.
During DNA replication, both strands of the double helix act as templates for the formation of new DNA molecules.
Both sides of the DNA.
Copying occurs at a localized region called the replication fork, which is a Y-shaped structure where new DNA strands are synthesized by a multi-enzyme complex.
Enzymes.
Here,
Remember
the
that.
DNA to be copied enters the complex from the left. One new strand is leaving at the top of frame, and the other new strand is leaving at the bottom. The first step in DNA replication is the separation of the two strands by an enzyme called helicase.
Helicase. Remember
This
that.
spins the incoming DNA to unravel it at 10,000 RPM in the case of bacterial systems.
10,000 RPM.
The separated strands are called 3' and 5', distinguished by the direction in which the component nucleotides join up.
Now check this out.
The 3' DNA strand, also known as the leading strand, is diverted to a DNA polymerase and is used as a continuous template for the synthesis of the first daughter DNA helix.
Polymerase, remember that.
The other half of the DNA double helix, known as the lagging strand, has the opposite 3' to 5' orientation and consequently requires a more complicated copying mechanism. As it emerges from the helicase, the lagging strand is organized into sections called Okazaki fragments.
That thing.
These are then presented to a second DNA polymerase enzyme in the preferred 5' to 3'
So
orientation.
it reads it backward.
These sections are then effectively synthesized backwards. When the copying is complete, the finished section is released and the next loop is drawn back for replication. Intricate as this mechanism appears, numerous components have been deliberately left out to avoid complete confusion.
Oh, man. So, vast quantities, a single cell's DNA would fill thousands of volumes of books with information, okay? And you can see how specific it is, and we'll talk about those enzymes more in a minute. But, okay, so this is how proteins are formed in living cells. What if we tried to form a protein without information, randomly, by assembling the needed building blocks, amino acids, supplying sufficient energy, and allowing them to bump off of each other and react at times in different ways? Okay?
What are the odds a single protein could form exclusively through the blind interactions of chemistry? Our target is one smaller than average molecule made from 150 amino acids.
It is pretty small.
Each aligned to ensure a folded chain. Researchers have calculated that on the ancient Earth, the probability of success was 1 chance in 10 to the 164th power. But despite these enormous odds, some theorists argue that given enough time, anything is possible. Okay, let's test the validity of this opinion. We'll begin by establishing an ideal environment for chemical evolution. An imaginary world that will provide chance with every opportunity to succeed. First, we stock the oceans to capacity with amino acids. That means all the atoms on Earth, including its entire supply of carbon, nitrogen, oxygen, hydrogen, and sulfur, are available to form 10 to the 41st complete sets of the 20 types of amino acids used to build proteins. Then we'll alter the laws of nature to protect these building blocks from the destructive rays of ultraviolet light and chemical contamination.
Boy,
in the
they're really making
primordial
it
soup.
easy. No UV?
Now let's turn the chemistry
contamination?
loose and see what happens. The amino acids start bonding furiously. In our experiment, an entire chain of 150 units self-assembles in only 1 second.
Well, you see that it takes longer than that.
Since all 20 types of amino acids are available, at the majority of sites, there is a 5% or 1 in 20 chance the correct molecule will align in the chain. If the sequencing is incorrect, the chain is immediately destroyed and a new assembly begins.
Every second. In 10 to the 41 sets. of
Throughout the
amino
planet,
acids.
6,000 million billion trillion attempts will take place every minute.
Every minute. Every minute.
That means in 4.6 billion years, the oldest estimated age of the Earth, the number of chains that don't fold will exceed 10 to the 58th power. It's a staggering total, but nowhere near 10 to the 164th. The trials necessary, on average, to build a protein of 150 amino acids by chance. So if undirected chemistry can't produce our coveted molecule during the entire history of the Earth, then how much time would have been needed? To find out, let's take a road trip. We'll start by erecting a bridge that spans the diameter of the observable universe, a distance of more than 90 billion light years. Then we'll place an amoeba on one end of the bridge. This single-celled organism will travel at the breakneck speed of 1 foot per year. It's off. While we wait for one protein to form, by chance, the amoeba slides along for more than 5 billion years to cross the entire universe and then return. But this race is just getting started. For the next trip, we'll add a payload, a single atom. After inching its way another 500 billion trillion miles, the amoeba drops off its cargo and returns for more. Will it get back before our lucky protein forms? Absolutely. In fact, it will complete another 10 round trips, then 20, 100, 1,000. And there's still no sign of a usable molecule. The amoeba continues making round trips until it has hauled off every atom on Earth. Then, all of the atoms in our solar system. Then, every planet and star in the Milky Way galaxy, one atom at a time. In fact, as we wait for one protein to self-assemble, the amoeba has so much time that moving at just 1 foot a year and carrying one atom per round trip, it will transport the entire universe more than 56 million times.
Holy shit. That's a long time. Still, maybe this 10 to the 161st is wrong. Maybe it's less than that. It's not too hard to figure out. I did it on my Excel sheet today. Just first line, 20. Second line, 20 times 20, right? Third one, 20 times 400. And so forth. You'll just see it branch out by the bottom. I couldn't even count the zeros, but that's how they figure. That's the probability. But maybe we could be lucky. It's possible. We're saying that's the likelihood on average for how long it would take to form a protein randomly. But it could happen by the first trial. It's possible to happen the first trial. The problem is that really solves nothing. We're not just creating a single protein. We're talking about life, okay? You're nowhere near life, just even if you had produced that protein.
Now, suppose against all odds, chemical evolution produced our single functional protein. Would we have life? No. We'd have one protein, just a lifeless arrangement of amino acids. The simplest living cell we know has more than 300 different proteins. But the proteins are only part of the story when you consider any actual cell. Remember, you're going to have carbohydrates, complex sugars, nucleic acids, DNA and RNA, lipids, a whole variety of different chemicals which jointly constitute the living state. Those bits and pieces all have to be brought into the same microenvironment at the same moment in time.
Each chemical building block must then be assembled and organized into the network of molecular machines that will control every facet of life.
If we can appreciate exactly how hard it is to produce one molecular machine using nothing except atoms and energy, we can see that there's a profound problem, because once you have one molecular machine, you don't have a living thing. These molecular machines need other molecular machines. And even if nature was capable of producing all the molecular machines necessary, that still wouldn't be enough. They have to all be together, all in this tiny little membrane-bound space that we call a cell.
From my understanding of what it takes to make a cell, it has to happen all at once. You can't do it one bit at a time, because everything works together in a causal loop. The higher level of organization transcends the pieces. The spatial organization in the cell requires that molecules end up in the right place at the right time. The DNA is copied into RNA. The polymerase that does the copying has to find the right spot in the DNA to start copying. The RNA has to somehow hook up with ribosomes, which have to be in a particular place. And the proteins then that are made have to be going to a particular place. That's an awful lot to account for by random chance.
The probability that you would get them in the same space at the same time becomes beyond unimaginable. And the probability that you would get them within a membrane enclosure, like a cell, is the next best thing to impossible.
Pretty much. These are a couple of rock outcroppings. You can kind of see a human face possibly there. It's hard to say whether these are designed or not. It's sort of like a human face when you look at it from one angle. Whereas when you look at this one, definitely designed, right? Because it looks exactly like a human face from any angle. And so the specificity involved, the level of specificity is part of what goes into determining the presence of design. We all know that Mount Rushmore was designed, and we would know that if we came here as an alien, never saw it before, never saw a U.S. president. We could look at that and say, somebody carved that, no problem. And then, though, when it turns out that they not only look very human, but that these faces closely resemble a number of U.S. presidents, all possibility for chance is gone. Because what would connect, whatever, erosion or whatever caused this to happen, what would connect that with an unrelated thing, such as the human faces of presidents? The chance of this being a natural formation goes to zero at that point, because it has a semiotic aspect. It's a symbol. These are pictures of something else. They refer to something outside of themselves. That's not possible under natural processes. It is only possible when you have designers setting it up. A human language is this way. A computer language refers to operations that are symbolized as a semiotic. It's only found from intelligence, only found in a design. We've never seen any example of it otherwise. And yet when we come to the cell, we are seeing exactly that DNA strand referring to something outside of itself. The protein. It sends the message with the RNA to the ribosome. The ribosome has no information, doesn't know what to do. It has to be told by the RNA what to do. The DNA knows what to do, but it can't do anything. It has to send out and get the ribosome to do the work. So you have one elaborate system for constructing the proteins, the other with the information. Neither can exist by themselves. They have to both be there. And that was that one guy's point, is you got to have all of these things. What's going to power it? You got to have mitochondria to provide energy. Oh, no, this is, whoa. Okay, there's more. We're not done. A huge hurdle to the natural formation of complex molecules is that most of the reactions involved here are either uphill thermodynamically, or they're less favorable than countervailing reactions. Uphill thermodynamically. Imagine burning a log, a piece of wood. It gives off heat. It's an exothermic reaction. And those gases go out. There's some ash left afterward. Now, if we capture the gases, we capture the ash, and bring them back together, we want to make them back into wood again. You can't really do that because that would be, the burning of the wood was downhill thermodynamically, but reassembling it would be uphill. Water doesn't run uphill. In thermodynamics, you don't see things that are disadvantageous thermodynamically don't happen. It always goes in one direction, not in the other. However, life is different in this regard. A tree could take those ashes and those gases and could reform them into wood again. And that action would be uphill thermodynamically, but the way that life gets around this conundrum is it uses something called enzymes, which have come up a few times tonight. Enzymes, macromolecules, some of the most complicated molecules that exist. And they can take compounds that don't want to bond with each other and drive them to bond anyway using energy from an unrelated reaction. Here's human glycolase. Thousands of atoms. This is a typical enzyme. And we're reading here from Wikipedia, which has a nice article if you want to read an article on enzymes. Most enzyme reaction rates are millions of times faster than those of comparable uncatalyzed reactions. To catalyze a reaction means to speed it up or slow it down, but in this case, speed it up. You're driving that reaction to happen. Enzymes can couple two or more reactions so that a thermodynamically favorable reaction can be used to drive a thermodynamically unfavorable one. For example, the hydrolysis of ATP is often used to drive other... ATP is like the batteries of the cell. And it's an unstable compound, which an enzyme carries up to the point where the reaction needs to happen and lets off a phosphate and goes to diphosphate, and a little burst of energy comes out. And it's directed right in where the reaction needs that energy to make it happen. So you're putting energy in. Endothermic reactions. Yeah, pretty amazing. They point out that enzymes can catalyze up to several million reactions per second. For example, uncatalyzed decarboxylation of that has a half-life of 78 million years. However, when the enzyme that is added, the same process takes 25 milliseconds. Whoa! So if you had that compound in a beaker, you would sit there for 78 million years before half of it had bonded or been decarboxylated. And, or you could add this protein and the same process would take 28 milliseconds. Less than a tenth of a second. Oh my God, that's astonishing. It's like magic. These enzymes, here, watch out for bias when you read on these subjects. Here's Jesse McNichol, who's a big proponent for chemical evolution. Slips in a little brief in this quote. He's talking about the triumphs of prebiotic chemistry. He says, under environmental conditions requiring quick replication, the RNA strand will, given adequate supplies of its building blocks and the addition of a polymerase, become progressively shorter as selection acts on it for maximum reproductive speed. See the little phrase he threw in? And some polymerase. So here are scientists trying to combine vast quantities of exactly the needed chemicals together. They can't get them to bond. Of course, we threw in a little polymerase. Polymerase is an enzyme, big one, 10,000 atoms, arranged just so. This was what was on that, coding the DNA strands as it went out. Every one of these is incredibly complex. The helicase, this is the thing that was spinning at 10,000 RPM. Your car engine would throw a rod probably if you went 5,000 RPM. This is going twice that speed. And chopping the DNA in half as it goes down. Really amazing stuff. Here's ATP synthase. This is the enzyme that produces the ATP, the batteries. This is the power pack of the cell. They form in dimers with two of them together. The atom count here is 75,600 atoms arranged very precisely so that it can produce that ATP and take it over to other enzymes to be used in reactions. The complexity goes all the way down, and it just gets worse the closer you look. This is also why cells have membranes. A membrane is an extremely complex shield that envelops the environment where all this life chemistry is going on, because these compounds are fragile. They're easily destroyed by other compounds, and they have to be protected. And this is what a cell membrane or a cell wall, in the case of plants, does. And it only lets through beneficial compounds, and it also gets rid of the trash that is left over after molecules break down. Let's do a little bit of cell division. Okay. Special fibers called spindles. Fibers form in each of the cells and grow toward the DNA chromosomes. That is not accidental. That's not a coincidence. They come down to the chromosomes and they attach onto the centromeres. And then they begin to pull. The two chromosomes have duplicated themselves, and so that both are identical. They pull them all apart, and they go back. The last phase, the cell divides, and we now have two cells. I just gave you the last part of that, the elaborate lead up to that, but I thought it was a cool part. Let's zoom in a little closer still, very close, right down where those strands are coming down the microtubules to the chromosomes.
So this is a single chromosome, and you have two strands of DNA in each chromosome. One is bundled up into one sausage, the other strand is bundled up into the other sausage. These things that look like whiskers that are sticking out from either side are the dynamic scaffolding of the cell. They're called microtubules, but the name's not so important. But what we're going to focus on is this red region. I've labeled it red here, and it's the interface between the dynamic scaffolding and the chromosomes. It is obviously central to the movement of the chromosomes, but we have no idea really as to how it's achieving that movement. We've been studying this thing called the kinetochore for over 100 years with intense study, and we're still just beginning to discover what it's all about. It is made up of about 200 different types of proteins, thousands of proteins in total. It is a signal broadcasting system. It broadcasts through chemical signals telling the rest of the cell when it's ready, when it feels that everything is aligned and ready to go for the separation of the chromosomes. It is able to couple onto the growing and shrinking microtubules. It's transiently, it's involved with the growing of the microtubules, and it's able to transiently couple onto them. It's also a tension sensing system. It's able to feel when the cell is ready, when the chromosome is correctly positioned. It's turning green here because it feels that everything is just right. And you'll see that there's one little last bit that's still remaining red, and it's walked away down the microtubules. That is the signal broadcasting system sending out the stop signal, and it's walked away. I mean, it's that mechanical. It's molecular clockwork. This is how you work at the molecular scale. So with a little bit of molecular eye candy, we've got kinesins, which are the orange ones. They're little molecular courier molecules walking one way. And here are the dynein. They're carrying that broadcasting system, and they've got their long legs so they can step around obstacles and so on. So again, this is all derived accurately from the science. The problem is we can't show it to you any other way.
Oh, man. Microtubules. And that's all actually there. It has to be put into animation because he explained earlier in the movie why the atomic microscopes, it's just doesn't suit itself to, but this is actually what's going on. Remember earlier we said living organisms have to be able to self-replicate. And that process that you're just looking at is part of the self-replication. How is a cell going to replicate without that complex machinery? They don't just fall apart. They don't just, molecules don't replicate themselves. They have to be made to do it by this elaborate machinery. Today, you hear a lot of people go on about the RNA world theory and how, there's all this RNA, and they found out RNA can catalyze reactions. So maybe there was just some RNA there, and then it just catalyzed the reactions, and then the RNA started to duplicate itself. Boy, I don't even know where to start. First of all, where the hell did RNA come from? That's like half of a DNA molecule. It's a super extremely complex molecule. It's only created in life. It doesn't happen naturally. It never occurs naturally. And the ribose backbone makes it break down easily in water. That's why you have to have a cell membrane. Here, there's no membrane. It's just happening out in the ocean somewhere or in the bottom of a pit or a hot thermal. All completely imaginary, never based on anything that we've observed. Yeah, RNA can catalyze certain reactions, but that has nothing to do with that. That's a different category than saying it can self-replicate. I see no chance of this ever coming to fruition. There's a 4-part lecture series by Jack Stoshak of Harvard on YouTube, which you can quickly find. And he goes through in 4-hour lectures, all of the progress of this nationwide project to discover the secrets of abiogenesis. And it's pathetic, frankly. I just couldn't believe how lame it was. You should watch it yourself and see what you think. He's like, here's a bubble. That could be a cell membrane. It's round like a cell membrane. A bubble is nothing like a cell membrane. Cell membranes are super complex, full of design. Implausible. Not plausible that this happened in the prebiotic Earth. This guy, a professor from Oxford, a British scholar, for decades, one of the leading attackers of theism. He's an atheistic thinker. He's written a score of books about how there is no God, and that theists are lame and they're irrational. And in 2003, he came out with a new book where he scratched out "there is no God" and put in "there is a God." And the subtitle is "How the World's Most Notorious Atheist Changed His Mind." He was like 80 at the time. He says, "I now believe that the universe was brought into existence by an infinite intelligence." He says the most impressive arguments for God's existence are those that are supported by recent scientific discoveries. The argument to intelligent design is enormously stronger than it was when I first met it. Yeah, I mean, this depth of complexity we're talking about is recent stuff. Even when I was in school, most of this was not known. There's been an explosion of discovery here, and it's a huge embarrassment, frankly, to people who are committed to naturalism. Let's go back to our argument. Our world does manifest the presence of design, that semiotic relationship. How would DNA ever connect itself to the formation of proteins that have nothing to do with it? That semiotic relationship. And therefore, a designer exists. Boom. And as we saw last week, it's also not just any designer. The designer has to fit what we're seeing. The invisible attributes, eternal power, divine nature. We can tell things about this creator that eliminate a lot of possibilities. The intellect there, Oh man, how about these? To fashion that, the will, the intent to create a plan like the blueprints for the Taj Mahal, except way more complex, way more complex. The forethought, to think about a plan and then put it into motion, all of these having to do with the personality, and right there, very many concepts of God that are pantheistic, that are merely impersonal, just simply will not explain what we're looking at here. You need a personal, infinite God. And so we talked about that last week. It's still right there, I feel, and there's multiple other areas we could go into that have to do with the argument from design. They say the earth has an iron core, molten iron, that spins at a slightly different rate than the exterior of the planet. I've never seen it. No one else has either. It's way too deep for us to get to. It's more than 2,000 miles below the surface. We can only drill 4 or 5 max. We never will see it. And yet, it's there. How do we know it's there? Because of the magnetic field around the earth. That's what it would take to create a magnetic field like that. And without that magnetic field, we wouldn't be sitting here. Our atmosphere would have been blown away like Mars's was. But so this works out real nice. We don't see the core. We can't feel it. We don't have a glass full of it. And yet we know it's there because we see the effects that it has. We see, and so too with a creator. Now we don't see the creator, but we see what he's done. This is Paul's point. Through what has been made. It's pretty obvious. Really obvious. And so that takes us back to the verse we read last week about people suppressing the truth. Sometimes people will look at something like this and they'll be like, whoa, that's really interesting. I'm going to have to think about that someday. You know, I'm busy right now. And they suppress the truth. They don't want to face what's right in front of them. And so I repeat what we said last week. God wants you to be honest with yourself, not to avert your gaze. When you get that sense that, oh man, I get the feeling this is true, this is actually true, well then, you should have the integrity to act on that. You should have the integrity to call out to God and say, if you're there, if I'm somebody created, you know, in your image, if it's possible to know you, how about it? I'm ready. What's going to be the danger in that? Why not? If God's there, that's pretty important. And the Bible says the people that call out to God will be answered, that he'll answer them. That he actually loves us and wants a relationship with us. We got another week to go on this. This is pretty good, Origin of Life. Very persuasive to me. I'll never believe that happened by accident. But you also have evidence inside of you that may be just as strong. And we want to look at that next week. Something that every one of us can check out for ourselves. You don't have to be a scientist. So I hope you come back for that. Let's draw a line there for tonight.